Okay, so in this video we're going to be doing radicals. You can see that we have an audience here. I do math and you can do anything. Okay, radicals. So I've mentioned a lot over the last few times that radicals are actually exponents. So let's take a look at this. If we have the square root of x, this is actually x to the 1/2 power, okay? And so anytime that we have a radical, it can be written as an exponent, which is why I kept saying that the rules for radicals are the same as the rules for exponents. Anything that we can do with radicals, with exponents, we can do with radicals, okay? So we can distribute. So if we can distribute with exponents, then we can also distribute with radicals. Okay, let me clarify some of this in terms of definitions before I go further into this. I should have done that. I'll put this off to the side. If we have a radical that looks like this, okay? So just some terminology first. What's under the radical is called the radicand. Okay, this number here, the n, that's called our index. And the symbol that you see here that we keep saying radical, that is a radical. Okay, radical is just anytime you see this symbol here. Okay, let me make, this is just a parenthesis. I want to make it a little bit clearer. It got a little off center there. So whenever you see a symbol like this, we're saying that we're working with radicals. Here, the index is what's inside of here. So the n would be the index. Now typically, I'll put this in the same color that I put the index in, which is not that color, it's this one. So the index, if there is no index, the index is 2. Okay, so that's by default. It's the same way that if we have an x and there is no power, it's x to the first power. Here it's the same thing. If we don't have something, then we're talking about the square root of x. It's an invisible index. It's because most of the time we're talking about square roots. Okay, so most of the time we don't need an index. But there are going to be a lot of times we're going to talk about them in this video where our index is actually a number. Okay, so if we have x to the n, not x to the n, but the nth root of x, then that would be x to the 1/n. Okay, so we also call this the nth root of x. We're talking about the nth root of x. So here we're saying the nth root of x can be rewritten as the exponent x to the 1 over n. And here what we're saying is the nth root of a times b is the same thing as the nth root of a times the nth root of b. So we can distribute. Again, this is like saying if we have the square root of a times b, that's ab to the 1/2 power. So we can switch anything to a power. And what that means is that we have a to the 1/2 times b to the 1/2. This is definition of exponents. Well, one of the properties of exponents. We can distribute, okay? So that's what we're doing here. So from there, we can get another distribution. We can say that the nth root of a over b is the same thing as the nth root of a over the nth root of b. Okay, so notice that you want to be really careful. This is not n times the square root of a over b. This is the nth root. The n should go inside that little v that you see there. Okay. Okay, so, and in this one, I want to just point out, and you're going to see this later when we are using fractions and things. One thing that we would want to put in here is we would want to say where b is not equal to 0, because if b were equal to 0, then this would be undefined. So we want to make sure that we say that, okay? Okay. So let's go in and start working with radicals. Let's say that we're talking about the 5th root of 32. So the 5th root of 32 is 32 to the 1/5 power. And 32 to the 1/5 power, if you put this into a calculator, is 2. But there are some things that you probably want to remember when we're dealing with radicals, okay? We probably want to remember some of the different powers of 2. So 2 squared is 4. This is something most of you know. 2 to the 3rd, also something a lot of you know, is 8. It would be helpful if you knew that 2 to the 4th was 16 and 2 to the 5th was 32. I would probably even go to 2 to the 6th as being 64. Okay, for the 3's, it would be helpful for you to know that 3 squared is equal to 9. These are things that you can always put into your calculator and figure out. But if you know these things here, it can make your life easier because you're doing a lot of the math more quickly. It's kind of like when we were talking about your multiplication tables, okay? So 3 squared is 9, 3 cubed is 27, and I would say you would also want to know that 3 to the 4th is 81. I would say you want to know that 4 squared is 16. You want to know all of the squares, okay? We talked about that when we were simplifying radicals, that knowing the squares up to even 12 squared is helpful. So the 2 squared, 3 squared, 4 squared, no 5 squared, okay? 4 cubed is 64. These are the things that you're going to see most in your square roots. So after this, if you have to plug into your calculator, it's not such a big deal because you're not going to see it that often, okay? So the 5th root of 32 would be the same thing as 32 to the 1/5. This is helpful just in terms of plugging it into your calculators. A lot of times you won't see a 5th root, but you will see something like x to the y on your calculator. I'll put that here. So on your calculators, this is on scientific calculators, even on graphic calculators, you're going to see x to the y. And this is where knowing that this is 32 to the 1/5 is helpful. Because you would in 32 to the 1/5. So this is just on your calculator. We typically don't write exponents with the little caret. That's only for calculators and for typing. Okay, we wouldn't write it that way in math. You would always write it like this. But on your calculator, you would write it as 32 caret. And remember, you need to write the 1/5 in parentheses. Order of operations, your calculator follows the order of operations. So if you don't put in the parentheses, it's going to do 32 to the 1st power, and then it's going to take that and divide by 5. Okay, and you don't want that. So it's 32, and then you're raising it to the power of 1/5. And this is how you would do it on your calculators. Okay? Okay, so let's talk about how we would simplify square roots. Not square roots, but radicals when our index is something other than 2. Okay? So simplifying radicals when the index, remember our index is n. These lines just appear out of nowhere. So when the index is not equal to 2, okay? So a couple of rules. There shouldn't be any fractions under the radical sign. So we're going to get into how to get rid of that. The first set of radicals that we simplify, you're not going to have any fractions. And when we say under the radical, that's the same thing as saying in the radicand. Remember, the radicand is what's under the radical. There's no particular order to this. This is all just, we could do this in any order. When we were simplifying exponents, we really cared about the order. Here, it probably doesn't matter that much. Okay. The rational exponents are all going to be less than 1. In other words, if we changed everything that's under, if we changed the radicand so that it's not under a radical, removing the variables, the exponents of the variables would be less than 1. And again, right now, seems very like in the air. We're not really sure what this means. As soon as we start working with something concrete, then all of this will make sense. So if we remove the variables from under the radical. And when we say there should be no fractions under the radical, that's also saying there are no radicals in the denominator. So I'm going to add to this because it's part of the same thing. And in the last unit, when we were finding roots of quadratics, if you remember, there were a lot of cases where there was a radical in the denominator, like for example, when you were finding roots, when you were completing the square, or you were finding roots using the quadratic formula. A lot of times you had radicals in the denominator, and I said, for now, leave it like this. After we go through this lesson and potentially the next lesson, you should be getting rid of all of those radicals. That would no longer be an acceptable answer. So again, the idea is that when you divide, that's a very complicated thing to do, to divide. We don't want to add something else that's even more complicated, which is to take a root, whether it's the square root or the nth root. Those things are difficult to calculate. The idea of simplifying is taking difficult calculations and getting rid of them, making them easier. Okay, so let's just take some examples. And it's going to take a couple of examples for you to get the hang of it. But then once you get the hang of it, this is a very simple process. Everybody loves it because it is so simple to go through it. Okay, so we're just going to go through a bunch here. Let's start with the cube root of x to the 6th y cubed. Okay. And in order to simplify this, essentially what we're doing is we're taking, this is a 6, by the way. Okay. Essentially what we're doing is we're taking these exponents and we're dividing by the index. And the reason why we're doing that is that this is the same thing as x to the 6th y cubed raised to the 1/3 power. So we can distribute that that exponent and we wind up with, I'm putting in a lot of extra steps here, but you should know that you can completely skip these 2 steps in the middle and go straight to the last step. So this is x to the 6th. That just appeared. This is x to the 6th. Over 3. And then y to the 3 over 3. Okay, because 6 times 1/3 is 6 over 3. 3 times 1/3 is 3 over 3. Remember, this is like 3 over 1 times 1 over 3. That's why we get the 3 over 3. You multiply the numerators and you multiply the denominators in a fraction. So 6 over 3 is just x squared. And 3 over 3 is y to the 1st. And I'm going to put in the 1. But remember, we don't really need the 1, okay? So we would really write this if we want to be 100% correct in the math. We would write the y without the power. And you can go straight from this step to this step, okay? And what we're doing when we go from that step to the other one is we're taking the exponents of the variables and you're dividing by the index. So divide the exponents of the variables by the index. And that's how we simplify a radical with an index that's not 2. Even if the index were 2, you would be doing the same thing, okay? So if we had, for example, we can do something very similar. we haven't really worked with radicals or square roots that had variables raised to powers. So let's say that we had x to the 14th, y to the 10th. We can go straight to from there to x to the 7th over times y to the 5th. Okay, we took our exponents and we divided by our index. So remember, our index is 2. If there is no index, the index is 2. And we're saying 14 over 2 is 7. And 10 over 2 is 5. Okay. Okay, let's take some more examples. We're going to do a bunch of them. So right now, all of these are perfect roots. Okay. X to the 6th, y cubed is a perfect cube root. So a third root is also called a cube root. So this is a perfect cube root, or a perfect third root. What we mean by that is that when we simplify, we can get rid of the radical entirely, okay? 6 and 3 are both divisible by 3. This one is a perfect square, okay? 14 and 10 are both divisible by 2. Right now, we'll actually work with ones that are perfect n roots, nth roots, just so that until you get the hang of it, and then we're going to put in some others that aren't, okay? So let's say that we had the 4th root of, and I'm going to change that color and make our radical a little nicer looking. So let's say that we have the 4th root. And I'm going to put the number 16 in here. And then we'll also put x to the 28th, y to the 20th, and let's do z to the 16th. Okay. So 16 is a perfect 4th root. If we go back here to the previous page of notes, 2 to the 4th is 16. Okay, so we can say that the 4th root of 16 is 2. Okay, so this one comes from the fact that 2 to the 4th is 16. That's where that came from, okay? So for these, you're not doing division. You are not doing 16 divided by 4. 16 is not an exponent, so you would not divide. Okay, you're only dividing the exponents by 4. Okay, it's non-exponents, so you wouldn't divide. It's an actual number, okay? You only divide the exponents by the index. So that's where this 2 comes from. We take 16 and we say, what to the 4th power is equal to 16? And it's 2 to the 4th power. Okay. Now for all of the others, we're just going to divide the exponents by 4. So 28 divided by 4 is x to the 7th. It's 7. So this would change to x to the 7th. $20 divided by 4 is 5. And 16 divided by 4 is 4. So this would be our final answer. Okay, so we took each of the exponents and we divided by 4. So I'm not going to write this every time, but I'll write it here so that you know where these came from. So 28 over 4 is 7. 20 over 4 is 5. And 16 over 4 is 4. That's where the 7, the 5, and the 4 came from. Okay, let's take another example. This is going to be our last one where it's going to be a perfect root. So this is a perfect 4th root. We were able to get rid of the radical entirely. Okay, let's take the cube root. Notice right now, I'm keeping our index relatively small. It's not always going to be that way, okay? Let's take another example where we have a number in there as well. So let's take 64. Let's do x. Now I'm using x, y, and z. They could be any letter, so we'll do more examples where it's any letter. We'll do x to the 12th. Y to the 21st. Okay. So what we're doing is we're looking for a number that raised to the 3rd power gives us 64. And we know from previously that's 4. Okay, we had that listed on the previous page. And then we're going to take our exponents and we're going to divide them by 3. So 12 divided by 3 is 4. And 21 divided by 3 is 7. So this gives us 4x to the 4th, y to the 7th. Notice this is a 1-step process. You don't need to include a lot of steps here. Okay, and again, last time, I'm going to put this in here. The 4 comes from the fact that 4 to the 3rd power is 64. Okay, so 64 is not an exponent, so you wouldn't divide by 3. You're looking for something that to the 3rd power gives you 64. And then here, we're taking the exponents and we're dividing each of the exponents by 3. That's how we're getting the new exponent. Okay, that's how we're getting our answers. Okay, now let's take something that isn't perfect. So let's start off with squares, okay? Square roots. And this is no different for, if the index is 3 or it's 4 or it's 15, it doesn't get any harder. The things that we do are exactly the same, okay? So we're going to start with squares just because it's something that you're a little bit more familiar with. So let's do 12, x to the 7th, y to the 9th. And the way that we do this is the same every time. We're going to break this up into 2 radicals. So this is actually a 2-step process. No matter how complicated this looks inside, it's always going to be a 2-step process. We're going to have 2 radicals. If we have an index, don't forget to write the index. And the first radical are going to be our perfect nth roots. Okay, in this case, they're perfect squares. And these perfect squares are factors of the radicand. the second radical that you see is what's left over. So remember, 12x to the 7th y to the 9th is the radicand. The radicand is what is under the radical, okay? This radical is just what's left over. Essentially, these are all of the things that we can't simplify. So we've done this with square roots before. We've looked for factors of 12 that are perfect squares. And a factor of 12 that's a perfect square is 4, okay? So 4 is the factor that's a perfect square. I'm going to put that in black. 4 is a factor of 12 and it's a perfect square. So that goes under the first thing. Now what's left over, what we would multiply by in order to get 12 is 3. Okay, 4 times 3 is 12. Same thing is true for x to the 7th. We're gonna pull out a perfect square. So the way that we do this is we want to figure out what's an exponent that's divisible by the index. The highest exponent that's less, or really the highest number that's less than the exponent and divisible by the index. So the highest number that's less than the 7 and divisible by the index, which is 2, we just go down. 7 is not divisible by 2, so we know that we're not going to pull out an x to the 7th. But 6 is divisible by 2, so we're going down. We're just doing 7. We start at the exponent, and then we go down by 1. 6 is divisible. So because 6 is divisible by 2, by the index, we're going to put it under the first radical. We put in x to the 6th. Okay. And what's left over? Well, we have 6 x's, so we need one more. That's what's left over here. And if we multiply x to the 6th and x to the 1st, based on the property of exponents that says that if the base is the same, you add the exponents, x to the 6th times x to the 1st is x to the 7th. Okay, so we just broke up the x to the 7th. Now we're going to do the same thing with the y to the 9th. So we start at the 9 and we say, is it divisible by the index? Which is 2. 9 is not divisible by 2. So we go down by 1. Is 8 divisible by 2? Yes, 8 is divisible by 2. So we're going to put a y to the 8th here. And what's left over? Well, we have 8 y's. We need one more. So we just leave it as 3xy. Okay, so what we're looking for for the variables, we are looking for the highest number that is less than or equal to. So it might be the exponent itself. And divisible by the index. This is the perfect nth root. Okay, so again, we're looking for the highest number that's less than 7 and divisible by 2. So 7 is not divisible by 2, but if we go down by 1, 6 is. So x to the 6th goes under the first radical. What's left over? 1x. So x to the 1st goes under the second. Then we do the same thing for y to the 9th. We say, okay, let's start at 9. And let's go down until we find a number that's divisible by 2, which is our index. So 9 is not divisible by 2, but 8 is. So we put y to the 8th under the first radical, and what's left over? Y to the first. Okay, now we just need to simplify this radical here. So we need a number that squared gives us 4. So 2 squared gives us 4. So we just have a 2 here. Then we do exactly what we did up here. We're going to take our exponents and divide by the index. So 6 divided by 2 is 3. 8 divided by 2 is 4. This we can't do anything with, so we just leave it. It's just the square root of 3xy. Okay, and this is just something about handwriting. I know sometimes it's not going to be 100% clear here, so I want to mention it. That's just because, we're doing this with computers and not on an actual board. Make sure that this exponent doesn't look like an index, right? The index of this radical is 2, so just be careful. I think it's pretty clear here. The 4 is the exponent of y. It's not the index of the radical, okay? This is it. This is as hard as it gets. So let's take one where instead of a square root, we have a cube root. So we're going to take another example. Cube root, and let's start using different letters because I'm a little tired of the x, y, and z. Let's say that we have cube root. Notice that we say cube root, but if it's index of any other number, then we don't have names for it anymore. So we would just say 4th root, 5th root, 6th root. So here we have cube root, but we could also say 3rd root. So we have a to the 6th, b to the 10th, c to the 5th. So this is a 2-step process. It's always only a 2-step process. That's why we think of this as so simple, because we don't have a lot of steps. It's short. So we have cube root, we have our perfect cubes, and we have what's left over. Okay, and I'll remind you of that here. These are our perfect cubes, or our perfect 3rd roots. And this is going to be what's left over. So now we're going to go back to our variables, and we're going to say a to the 6th. So we're going to start at 6, and we're looking for a number that's less than or equal to 6 and divisible by our index, which is 3. So we're going to start at 6. 6 is divisible by 3. So we're going to take a to the 6th and put it under the perfect cubes. And there's nothing left over, okay? All 6 of our a's are under this cube root, okay? Now we're going to do the same thing with b to the 10. So we start with 10. 10 is not divisible by 3. So we're going to go down by 1. 9. 9 is divisible by 3. So under this first radical, we're going to put b to the 9th. Okay, what's left over? Well, we have 9 b's over here, so there's 1 b left over. Okay, c to the 5th. We're going to do the same thing. We start at 5. 5 is not divisible by 3. We go down by 1. 4 is not divisible by 3. So we go down by 1 again. 3 is divisible by 3. So under here, the first one, we're going to have c cubed. And what's left over? 2 c's. 3 of them are under the first one. There are 2 left. I'm going to move this down here because I don't want it to interfere with what we wrote up here. So now we're just simplifying the first one, and these are all perfect cubes. So just like up here, we divide our exponents by our index. So 6 divided by 3 is 2. 9 divided by 3 is 3. 3 divided by 3 is 1. Notice we don't put a 1 here. Okay. And then the rest of it is to stay the same. So the what's left over just stays. We don't do anything with it. Okay. Okay, let's take another one. They're not really going to get much harder than this. This is essentially it. Let's take... let's take another... Let's take a 6th root this time. Okay, now I'm going to put a number in here. Typically, you're not going to have to use such large numbers. The 6th root, I know you're not that familiar with the 6th roots, and it might be a little bit brute force to figure out when there's a number under here, but I'm going to give it to you, and I'll help you with that part. So we're going to do 64, and then we're going to do x to the 8th. Y to the 26th, Z to the 13th, and just for fun, because we like having fun, let's add in a couple of letters. Let's say that we have A. I won't make these super large. Let's say that we have A to the 38th, and one more, we'll make it B to the 41st. Okay. Nothing is going to change here. We're going to have, so notice these are 6th roots. Okay, that's how we would say it. Our index is 6. So we're going to have two radicals here. Both of them are going to have indexes of 6. One of them is going to consist of our perfect 6th roots, and one of them is going to consist of what's left over. So hopefully I'm leaving enough room here. Okay, and we're just going to go piece by piece. So 64 is actually a perfect 6th root. 64 is 2 to the 6th power. So if you know that 2 to the 5th is 32, you might be able to see right away that 2 to the 6th is 64. Otherwise, you kind of have to just experiment. You have to do 2 to the 6th, 3 to the 6th, 4 to the 6th. Now, exponents grow very, very quickly. So if you have 2 to the 6th, if 2 to the 6th had not been 64, 3 to the 6th is going to be much, much larger, okay? 4 to the 6th is going to be huge. 5 to the 6th is going to be huge. So 64, you kind of know start at the lower numbers, okay? But it's brute force. If you don't know that it's 2 to the 6th, you have to just try lots of different numbers, okay? So 64 is a perfect 6th root. So it would go under here. There's nothing left over. Because it's a perfect 6th root, there's nothing left over. Okay, now we're going to do our exponents. We start at 8. 8 is not divisible by 6. Okay, so we go down by 1. 7, not divisible by 6. We go down by 1 more. 6. 6 is divisible by 6. And if you know your multiplication tables, this is not going to be very difficult for you. If you're not as familiar with your multiplication tables, use your calculator, okay? Just do 8 divided by 6. When we say something is divisible by 6, what we're saying is once you plug it into your calculator, you should get a whole number. And if you're not getting a whole number in an integer, then it's not divisible. So the smallest number, the largest number that's less than or equal to 8 and divisible by 6 is 6. We have 6 x's under the first, so there are 2 left over. 6 and 2 is 8, so you're just subtracting. So we're going to have an x squared under here, okay? Notice your exponents, add to the exponent here. We're going to do the same thing with 26. 26 is not divisible by 6. 25 is not divisible by 6, but 24 is. So we're going to have y to the 24th under here. And what's left over? There are 2 y's left over. Okay. Then we do the same thing with the z to the 13. 13 is not divisible by 6, but 12 is. What's left over? There's one Z left over. Okay, I'm gonna write kind of small here because I didn't leave enough space. 8 of the 38. 38 is not divisible by 6. 37 is not divisible by 6, but 36 is. So we're gonna have an 8 of the 36. What's left over? And an A squared. And B, 41 is not divisible by 6. 40 is not. 39 is not. 38 is not. 37 is not. But 36 is. So we're going to have a B to the 36 here. Okay, B to the 36. And what's left over? 5. So now we can simplify this first one. We only have to simplify the first one. The second one is just going to be what it is. So 64 to the 1/6 is 2. This is just going to be an X because 6 divided by 6 is 1. 24 divided by 6 is 4. So we're going to have a Y to the 4th. 12 divided by 6 is 2. 36 divided by 6 is 6, so we're going to have an A to the 6th, and we're going to have a B to the 6th. Then we have the what's left over. So we have an X squared, Y squared, Z, A squared, B to the 5th. And that's it. Okay. Let's take another one. I'll move to the next page. Let's do a 5th. And we're going to do 32. A to the 21st, B to the 33rd, and C to the 20th. Okay, so again, we're going to have 2 5th roots. I think I left enough room. If I didn't leave enough room in this one, I'll delete it and start over. Okay. So, I'm going to change this to 64, just because I want you to have experience when you have something left over. Okay. So, we're looking for a factor of 64 that's a perfect 5th root. 64 is 2 to the 6th. It's not a perfect 5th root. There's no number that when you multiply it by itself 5 times, you get 64. But there is a factor of 64 that's a perfect 5th root. 32 is a factor. So 32 is going to go under the perfect 5th roots. And what's left over? Well, 32 times 2 is 64. So the 2 is going to go under the second one. I don't think this is enough room, so I'm going to rewrite it exactly as it is. I'm just going to move it over. Okay. Okay. So now we're going to do the same thing with the exponents. We start at 21. 21 is not divisible by 5. 20 is divisible by 5. So we're going to put A to the 20th under here. How many A's are left over? 1. 33, not divisible by 5. 32, 31, not divisible by 5. But 30 is. So under here, we put B to the 30th. What's left over? a b cubed. C to the 20, 20 is divisible by 5. So the whole c to the 20 goes under that first fifth root. And there's nothing left over, okay? So we don't do anything here. There's nothing left over. So now we're going to simplify this first fifth root. So 2 to the 5th is 32. So we're pulling out a 2 from the 32. Notice we're not taking 32 divided by 5, okay? Then we divide 20 by 5. We get a to the 4th. 30 divided by 5. We get b to the 6th. Then 20 divided by 5. We get c to the 4th. And then the rest of it. So notice I'm leaving more of a space here. We have 2a, b, cubed. Okay, this is really nice. This is it. We're done. So this looks kind of complicated, but it's not. It's really simple. We're dividing it into perfect fifth root versus what's left over. Okay? Okay. Let's keep going. So, let's do addition and subtraction of radicals. Actually, let me stop here and we'll do addition and subtraction of radicals in a new video, just so that you don't have to listen for so long. And I'll do that in a new video with you. But you'll see it continue right on this page in the next video. Okay, so that's it for this one. This is just simplifying radicals that have indexes that are not equal to 2. And that's it.